So, hi AP Physics students. This is a problem I want to show you how I will solve it, and then I'll let you apply this same kind of technique to problem number 4 and problem number 5 for the homework. Here we are in the force problems review. Okay, so the idea is we have two masses, and they are one's on a smooth surface, and smooth is like code for friction free, and there's a pulley, friction free pulley. The two masses are tied together with a string. Mass M2 is pulling down, mass M1 is sliding across the surface. Again, the surface is friction free, so we don't have to worry about friction in this question. Okay. One thing I do want to point out is the acceleration vectors are here. This M1 is moving to the right and M2 is moving down. If it wasn't apparent, there it is now. Okay, so here's how we go about solving this problem. First of all, you can draw a picture if you would like. That's fine, but the picture was drawn on the problem. You don't have to redo that, but I do want everybody, the first step of every force problem really is a free body diagram. So we have an M1, okay, and then we have an M2. All right, now if I wanted to be kind of clever about it, if I wanted to be clever, I see that M1 is 5 kilograms, so and M2 is 3 kilograms, so I could do this. I could say M5 and M3, and that way I can still put my mass in there without having to put units. It's a subscript. All right. Let's see here. So what are the forces acting? And the AP requires that you only put forces on the free body diagram. So the forces, pulling down here, and a lot of students will write mg, and a lot of students would write mg here. And that's wrong, right? In that case, there are 3 m's. There's M5, there's M3, and then there's this ubiquitous M there. So be really careful. Make sure you label it with two masses. You got to make sure you know which mass we're talking about, the 5 kilogram, the 3 kilogram. All right. The mass on the surface has also a normal force going up. And if the AP gives you like a piece of graph paper grid superimposed on the diagram, what they're looking for is to make sure that you draw this vector here the same length as this vector. All right. Because the weight of the object should be offset by the normal force, because we're not accelerating up and down. And then the tension this way, the force pulling the 5 kilogram mass to the right is the force of tension, and do that. A lot of teachers, a lot of students, maybe even the AP answer keys, they will call this T for tension. I really recommend that you don't do that. Pretty soon, what we're gonna have a mass on a string, and there's going to be tension, and there's going to be a centripetal force, and there's going to be a period, and the period T for period and T for tension is going to get confused, and so don't do that. Call it FT. Let's be good about that. And so then the last force here is the force of tension on the hanging mass here. Now, it doesn't really matter how tall we draw these, but in reality, let's think about this. Is this the right size? Is compared to mg, should this be the same size? Should this be bigger? Should this one be smaller? Let's think about that in terms of our accelerations. We know that this mass here is accelerating to the right, and we know that this mass here is accelerating downwards. Notice I did not put my acceleration vectors anywhere near my blocks. I think the AP will count off if you even add it. So when you draw the free body diagram, for the love of all things holy, do not add the acceleration vectors on that first question. All right, but you can do it here with me. It's fine. All right, so I put this in to show you that if we accelerate this way, okay, the net force is ma, right? And so this net acceleration we know is going to be downward, and therefore negative. Now, could we make downward be positive? Absolutely, but with the Descartes system, we usually use downward to be negative, but you could absolutely make that be positive if that suits you. If down is positive, then this would be positive, this would be positive, and Ft would be negative. You would have to be consistent. So if the A term is downward and negative, then that means that this force here, the downward force, has to win over this one. This one has to be bigger than Ft. So if I were to do it, accurately, my Ft term should be smaller than my M3G term. Okay, but on a free body diagram, we don't care so much. We just, unless again, there's a little grid, a little graph paper grid, and then they do want you to be accurate. But here we don't care so much. All right, so here's the deal. The first thing you do is a free body diagram. Always, number one. Number two is we're going to apply Newton's second law. All right, and a lot of people, I'm probably making a lot of people mad, but I don't care. This is not Newton's second law. The force is not equal to ma. What Newton's second law says, and actually this isn't really even Newton's second law, this is a baby version of Newton's second law, but it says that the net force is ma. The sum of all forces is ma. Another way of saying net force is sigma F. That's how I like to write it, but you can write net force, sigma F, net force, total force, resultant force, sum of forces. All of these are the same thing. And so this is applying Newton's second law, but you have to apply it to each mass in each direction. And that's it. That's how you solve it. And then eventually you're going to get a system of equations, and it's just math at that point. But here's the physics. So we're going to apply Newton's second law. Hang on, let me adjust my camera here. Sorry about that. Sorry for the quality of the camera, quality of the microphone. I'm not in my usual studio. All right, so apply Newton's second law to the first mass. So let's look at M5 here, and we're going to look at the sum of the forces in the vertical direction, in the y direction. So what is the acceleration, and what is ma in the vertical of this one mass? All we're concentrating on is this mass here. We're ignoring this one. We're only concentrating here. So the acceleration up and down, of course, is 0. It's not bouncing up and down as it moves across the screen, as it moves across the table here. It is simply sliding across and not accelerating up and down. So this is pretty straightforward. The normal force here is positive. M5G is negative. So, normal force minus M5G equals 0. And we knew that, right? We probably, hopefully at this point, didn't even have to write this out, but just for completeness, all right, we end up with, the normal force is equal to M5G. This does not matter for this problem because really the normal force here is probably going to be used often when we talk about friction. And so that is problem number 4, So you will need this for problem number 4, but for problem 3, you probably don't need it. We're still on mass 1. This is our M5 work, okay? So now let's consider the horizontal direction. So we do it again. We apply Newton's second law. Sum of the forces is equal to ma in, I'm just going to be super obvious here, in the x directions, okay? And so now this means the sigma is the Greek letter sigma, and it means to add. It means to summation. And so we're going to add up all the forces in the x direction. There's only one, and we call it Ft, and it's going to the right, so we call it positive. Okay? There's only one a term here. There's only one acceleration. It happens to be in the x direction, so we're just going to call it ma. And that's it. That is one. That's the equation here. Okay? Finally, we're going to apply this, and this is where the hard part comes in. We're going to apply this to M3. So this is going to be our M3 work. So let's apply Newton's second law to M3. Okay, M3A. So we could write the y. There is no x component, right? So it's all y. We don't have to be so obvious about it, but we could have just written F. The sum of the forces is equal to M3A. And a lot of students will write this, and they're gonna miss it. This is probably the biggest mistake in introductory physics, is what direction is M3A? And that's why I draw this little arrow there. I draw it, and I even remind myself, hey, dummy, it's negative. Okay, so we need to put a little negative sign there. It is going down. That is a downward force. Again, if you want to make down be positive, that's fine, but then the up vectors have to be negative. So if we allow down to be negative, we would have Ft going up minus M3G is equal to minus M3A. Okay, and then we solve this for Ft. Why? Well, it's just force of habit, but you can see here in just 1 second why. So when I move this over, I'm going to have an M3G minus M3A. For all you math lovers out there, it's going to be tempting to pull out the M3. Don't do that yet. You'll just have to undo it in a minute. So now we have equation 1, equation 2, and equation 3. Again, equation 1 we're not really going to use until we get to frictions, usually, but sometimes we do. And notice this Ft and this Ft, that's the force of tension in the string, and the force of tension in the string is the same for both objects. It's the same string. That is not exactly why it's the same. You will learn this later on, why the tensions are the same. The tensions are the same because the pulley is friction-free and the pulley is massless. That's why, but we kind of gloss over it and we say, oh, it's the same string, so it's the same tension. That is not the case when you have a massive pulley and maybe the pulley has friction. So just be careful there, but this tension and this tension for our purposes are the same. So, I state the obvious all the time, Ft equals Ft, or maybe equation 2 equals equation 3, or somehow tell the AP that you know what you're doing. You're going to solve this system of equations by substituting. Oh gosh, I made a huge mistake. Look at it. Did you find it? I hope you're screaming at the screen. So here I used M5, there I used M5, there's M3, but look at that. This is M5. Oh my gosh, I'm so sorry. I don't have time to go back and fix it, but I just did. Okay, so that little guy there is, is really, really important. You can't just let it be M's. So when I write this down, and I should tell you too, I'm going to just double check here. This is going to the right, that's going to the right. Positive, positive. Up, well, I'm going to check here. So this is going up, that's pulling down, positive, negative, negative, and then I'm going to check my math. I do a double check here. Now, all of my pluses and all of my minuses are in. I've already accounted for the ups and the downs and the lefts and the rights. And so now from everything we do from now on is a magnitude. Okay, so we're going to find the magnitude of the accelerations. This acceleration and this acceleration are the same. This one was positive, this one was negative, right? But the the magnitude is the same. Okay, and the same is true with the tensions. All right, so we set these two equal, and so M5A is equal to M3G minus M3A. And what are we looking for? We're looking for A. Notice I haven't plugged in any numbers, right? Don't plug numbers in until the very end. So here's my terms, and so when I pull this over, I'm going to end up with an A, and then I'm going to have an M3 plus M5 is equal to M3G. And I know a lot of teachers will teach this as one system. Don't break it up into two masses. Treat it as one big system with an internal force, blah, blah, blah. It makes it really hard to solve more complex problems. So this is the way, this works for every single problem. We're looking for A. We're going to just divide by the two masses. Again, don't plug things in until the end. It's so much easier to write variables. All right? And here's the key. If you get, after all of that work, if you get the sum of the forces, in the denominator, you are probably going to get it right. And so there it is. And if you think about it, this is the net force acting on the system, the net force, this hanging mass is the thing that's making it move. If we got rid of this guy would not move at all. So this is the net force, and then we divide by the sum of the masses. That's kind of a cheap and easy way to do it, which works fine for some easy problems like this, but it will not work for complex problems. The last thing to do, of course, is to plug in. because I use subscripts 3 and 5, I don't have to go back and look to see that my masses are 3 kilograms and 5 kilograms. I just know they are because of the subscripts. Okay, parentheses, please. No dots, no X's. Gravity. I did that. Look at that. 9.8, not negative 9.8. G is always positive, and then the sum of the mass is 3 kilograms and 5 kilograms is 8 kilograms. And, you know, at this point, I don't even know what the answer is. I apologize for that. So let's see here. I've got 3 times 9.8. Oh, actually, I said, well, we can use 10. I think I said in the instructions you can use 10. The AP doesn't care. 3.75. And now what are the units? Kilograms cross out, meters per second squared. This is an acceleration. Oh, goody. That's what we're looking for, accelerations. So that's our answer. The acceleration is that. And notice that this is the magnitude. So when I come back up here, the acceleration of this mass is negative 3.75. It's going downward. And the acceleration of this mass is positive 3.75. It's going to the right. Anyway, that's a long way to answer a simple problem, but I wanted to show you all the little steps. But this is what we're looking for. Again, to recap, you must do free body diagrams. You must. On the AP exam, the free response questions are worth 15 points. The free body diagrams will be worth 3 points. All right, so that's a huge number. That's a huge number of points there, just to draw a diagram. Get it right on that, and then you will, you'll have better chances here to get the correct answer. Apply Newton's second law for each mass in both directions. Okay, mass number 1, mass number 2. Now, for this problem, I wouldn't necessarily need this because all of the motion is here, and again, we don't have friction. If we did have friction, the normal force would be important, and you could state this without proof. Like you just know if something's on the tabletop that force and that force are the same, so the normal force is equal to m5g. You don't have to write this out, but that's where it comes from. So we can ignore that if we want to, but all of this work here needs to be done. Okay? Don't even bother about plugging units in until the end. Use variables all the way through. Solve for your variables, then plug in your nose. Write down the answer with units. All right, thanks. Have a good day.